image and the direction of motion, speed and direction of motion of the image. See, I'm telling this to all of you. Some of you may be very comfortable with the mirror formula and all, but still visualize the ray diagram before you take any step in an optics question. Radius of curvature is 20, object is at 30 centimeters. So it's not given whether it's a point object or an extended object, and it's not necessary also. But visualize where the image is going to form roughly. Okay, then solve the problem. Sorry. Okay, I got one answer as 8, okay, maybe centimeters per second, but I don't think it will be that much. We'll see. Okay. One of you tell me, roughly where does the image form in this case? Just the location of the image. Between which 2 points does it form? Okay, Pradyun is saying it forms between focus and the center. Correct. Correct. See, radius of curvature is 20 centimeters. Object is at 30 centimeters in front of it. Means it's beyond the center. So it's this case. Okay, let me take this ray diagram. It's very important to visualize the ray diagrams before applying any formula. It will ensure that you don't make mistakes in your answer. And it will also give you some ways to check your answer. Okay. So listen, all of you, this is the case that we have to consider. It's not given to you whether the object is extended or a point object. Never mind, you can take it like this. So if object is beyond the center, image will form between center and focus. Fine. It is told to you that object is moving towards the mirror, and you are asked to find out how the image is moving, with what speed and in which direction. Okay, I got multiple answers. One has 0.5, one has 1 centimeter per second. We'll see. But let us do the visualization first. If object is beyond center, image forms between center and focus. And you know that if this is the object between center and focus, then this becomes the image beyond the center. Okay. So you can consider it as roughly 2 regions here. kind of complementary regions, I can say. From infinity all the way till here is one region, till the center. And from focus to the center is another region. When object is at infinity, image forms at the focus. That is how focus is defined. And when object comes closer, look at where the image closer means what? Object from infinity, it is coming towards the center, let's say. Okay, it's at this position. Then where is the image? From focus, it is going towards the center. So when object moves this way, image moves this way, opposite direction. So there we got the direction now. Okay. And object, when it comes from infinity to center, means it covers infinite distance. How much distance is the image covering? Focus to center, only the focal length. Okay, or half of the radius it is covering. So when object covers a lot of distance, image covers only a little bit of distance. So which one should be moving faster? Object must be moving faster. In this case, in this question. Okay, if object is beyond the center, image forms between center and focus. And if object is moving, image will be moving, and object has to move faster than the image. Even if we solve, we should get the same answer. We should get an answer where the image speed is less than that of the object speed. Okay, and notice one more thing. Object coming towards the mirror, image is going away from the mirror, opposite directions. Okay, so these two are one complementary case. Another case is this. When object lies between focus and pole, image is on the other side. Okay. Now, if object is exactly at the focus, image will form at infinity. And if object is within the focal length, okay, I'll roughly draw that here. If object is within the focal length, you know where the image forms. It will be forming somewhere here. So in this region between focus and pole, visualize what happens. As the object moves from focus to pole, okay, as the object goes this way, image comes from infinity to the pole on the other side of the mirror. These are complementary regions, you can say. But here, object and image cannot switch places. In the yellow region that I have shown, object and image can switch places. But in this red region, object image cannot switch. Object has to be between focus and pole. Image will form behind the mirror. But when object moves from focus to pole, image comes from infinity to the pole. So in this region, image will be moving faster. Okay, like if this is object and this is image. An object covers a small distance from focus to pole, image will have to come from infinity to pole. Image has to move faster. So if you remember this, if you visualize it this way, then you will be able to, in fact, from the options itself, you can choose. Otherwise, even if you calculate, it will avoid your, this visualization will help you avoid mistakes. Okay. Now, clearly the case we know, this is the object and this is the image. How to derive image speed when you know the object speed? The ones who have solved this question, Anugrah, how did you do it?
By differentiating the mirror formula with respect to time.
Okay. Okay. Isha, how did you solve?
So I just know the formula.
Okay,
Vi
fine.
is equals to minus mv naught.
Okay, in terms
V
of
of the
magnification,
object.
let it be. But it's better to know the derivation always. Now see, object speed, based on that we need image speed. Speed by definition is rate of change of distance. So object speed, okay, for speed I think we should use some other symbol. Let it be. V naught is the object speed, will be rate of change of object distance, because speed by definition is rate of change of distance with respect to time. And image speed will be rate of change of image distance. That's all. That is what we are looking for. So if you have a relation between u and v, you can differentiate it and get a relation between du by dt and dv by dt. That's the idea. And what's the relation between u and v? The mirror formula. 1 by v plus 1 by u is equal to, you can write 2 by r or 1 by f, anything is fine. Now here the object is moving. means u is a variable, object distance is a variable. So automatically image will move. So v also becomes a variable. But the radius of curvature of the mirror remains constant. You can be given problems where the radius is changing also. They can tell you that the mirror is stretching, its radius varies at this rate, then r will also be treated as a variable. For now, let's assume it's a constant. Okay, they can make the question as difficult as they want. What we are looking for is a relation between du by dt and dv by dt. So we differentiate this. Derivative of 1 by v, but with respect to time, it becomes minus 1 by v square dv by dt. And derivative of 1 by u, that too with respect to time, becomes minus 1 by u square du by dt. And derivative of 2 by r with respect to anything will be 0 because r is a constant. That's all. Remove the minuses. And there you have the relation between du by dt and dv by dt. Therefore, you can say that dv by dt, that's the image speed divided by v square. Actually velocity, this is actually velocity, not speed. Because v and u will take with signs, no? They can be positive, they can be negative. So it's like displacement. Okay. Or position, rate of change of position is velocity. And plus du by dt is nothing but, dv by dt is rate of change of image position, no, that is image velocity. And du by dt is rate of change of object position, so that is object velocity divided by u square is equal to 0. Therefore, image velocity becomes minus v square by u square object velocity. Isha, what was the formula you told? We'll just verify if it is correct or not.
So velocity of the image is equals to minus m of velocity of the object.
I think it should be m square of the magnification. Okay. Do it that way and check your answer. Fine. So here you are given the object distance 30 centimeters. Did any of you calculate the image distance? Tell me quickly. Okay. You have to use the mirror formula and calculate that first. Only then you can tell the velocity of the image. Let's do that.
Sir, 15 centimeters.
Plus 15 or minus?
Minus 15.
Okay, possible. Let me just quickly substitute here. 1 by v plus 1 by object distance. Here you need to be very careful. Sign convention is to be applied. Object is in front of the mirror. So rays will be going towards the mirror. In front of the mirror will be negative. So minus 30 is equal to 2 by radius of curvature is given 20 and it's a concave mirror. For a concave mirror, center will be in front of the mirror, center of curvature. So radius also should be taken negative. So that's like minus 1 by 10. Send it that side. Okay, we'll take Anugraha's answer. We get V as minus 15 centimeters. Put that there. Therefore, velocity of the image becomes minus V square by U square. You don't have to bother about the minus here because it's getting squared anyway. Multiplied with velocity of object. Object is moving at a rate 2 centimeter per second. So this becomes 1 by 4. 2 by 4 is 1 by 2. This is minus 1 by 2 centimeter per second. And the minus in the answer indicates that the image is moving opposite to the object. And that makes sense. We have visualized that also. If object comes from infinity to the center, image goes from focus to the center. They are moving in opposite directions. Okay, so if you substitute everything properly, you will get the answer along with the sign. But remember this kind of visualization. Depending on how the object moves, you can tell how the image moves. Where it forms and how it moves also can be told. Okay, so what are some of the ideas that we have used here? If object is at infinity, image forms at focus. As object comes to the center, image also comes to the center. That's one case. If object is within the focal length, image forms on the other side. So from focus, as object goes to the pole, image will come from infinity to the pole. Okay. So there are cases where object moves faster than the image. There are also possibilities where image moves faster than the object. Okay, and remember this point also. If object is real, image is real, then their positions can be interchanged. If object comes to image position, image will go to object position. Okay. Next. Okay, try this question, all of you. Simple question only, but I want to know how many of you will do it correctly. Object of height 3 centimeters is placed let's say 20 centimeters in front of a concave mirror of focal length 30 centimeters. Find out the properties of the image. Like, is it enlarged, diminished, real, virtual, upright, or inverted? Okay, what are the properties of the image? Derive the magnification and properties of the image. Okay, I got one answer as magnification +3. Based on that, you can tell. Okay. 1 by V plus 1 by U is equal to 1 by F. Rishi, tell me. What values will you substitute in the mirror formula? How much will you take U as? Pradyun, you can also tell. How much will you take U and F as?
Sir, U is -20.
Okay, in front of the mirror, -20. And what about focal length?
30, sir.
30. Okay. Anugrah, how much did you take the focal length as?
-30, sir.
Okay. So one of you has taken +30, one of you is taking -30. Why should you take -30 even when it is given +30 in the question?
So for concave mirror, focal length when calculated, it's from the mirror opposite to the incident ray direction, so it's negative.
Okay. Okay. See, this is what I wanted to highlight in this problem actually. In case of mirrors, they will always give focal length positive in the problem. If they give with negative sign, then you can consider yourself lucky. But generally, focal length is given with a positive sign, irrespective of the nature of the mirror. Okay. But you look at the like you imagine the diagram if you want. For a concave mirror, okay, the focus will be in front of the mirror. Now, mirror can reflect only on one side. Okay, like concave side is the reflecting side. If it has to reflect, rays have to strike the mirror. Means incident ray should be moving towards the mirror. Only then it can reflect. Incident rays should be moving towards the shiny side of the mirror. Only then it can reflect. Now, if incident rays are moving towards the mirror, then for a mirror, by default, behind the mirror will always be positive, and in front of the mirror will always be negative. It has to be like that. Okay. Same for a convex mirror also. Okay. Convex side. Okay. Yeah. The convex side is the shiny side. Now, if it has to reflect, rays have to strike the shiny side. Okay. So they should be moving towards the convex side. Then again, behind the mirror will be positive because that is the direction in which the incident rays are traveling. In front of the mirror will be negative, always. For mirrors, it's always like this. But the focus of a convex mirror is always behind the mirror. Always. It just depends on how the mirror is curved. Okay. Convex always has focus behind the mirror. That means it will always have a positive focal length. Like when you substitute in the mirror formula, you substitute positive. For concave, the focus is in front of the mirror. And front of the mirror is negative. So when you substitute the focal length in the formula, you have to substitute it with a negative sign. Even if they give it positive in the problem, they told you that it's concave. No, it has to be substituted negative. Okay, so indirectly they test that knowledge, whether you are aware of the fact that a concave mirror should always have negative focal length or not. They'll specify positive only in the question, but you have to substitute negative. Okay, make that correction, you will get the proper answer. Next case. A small object okay, let's take it as a small rod of length L is placed at a distance x in front of a concave mirror. Of focal length, let's say f. Calculate the length of its image. But I should say how it is placed. Small rod of length L is placed at a distance x in front of a concave mirror of focal length f along its axis, along its principal axis. Means the rod is lying on the axis. It's not perpendicular to it. Okay. Derive the length of the image. You're not told where exactly it is placed, beyond the center or between center and focus, or some part to the left of the center, some part to the right of the center. Nothing like that is mentioned here. So we need a general answer. Okay, I got one answer as f square L by f minus x whole square. We'll see. Let's imagine one such situation. Suppose this is the principal axis. Actually, principal axis has to be drawn after the object is placed. We know that. But let's put the object on this line itself. And assume the object is kept beyond the center. Okay. Maybe somewhat like this. It's a small object actually, but for our visualization, I have taken it significantly long. I'll mark one of its ends in yellow, one end in green. Okay. Now, first thing is visualization. We have to imagine how its image is going to get formed. This rod is along the principal axis. The width of the rod is negligible. For us to be able to visualize, I've shown it significantly. Can any of you tell me where its image will form? That's quite easy actually. Where will this?
Between F and C.
Between F and C. Okay. So you can imagine the image being formed like this. Which dot's image will be on the left? Which dots will be on the right?
The green dot will be nearer C. And
Near
the
to C. Okay. Yeah. See, we know that, like not in this case, but if it's a point object, we know that if object is at infinity, image forms at focus. And if object comes from infinity to the center, image comes from focus to the center. So farther the object, closer its image is to the focus. And nearer the object, nearer its image is to the center. It's like that. So for the yellow point, you take any incident ray like this, the reflected ray will be like this. Okay, and for the green one, you take the incident ray to the same point of incidence, the reflected ray will be like this. So the green dot's image will form here, and the yellow dot's image will form near the focus. That is the image of the object. Okay. Now you are told that the object's length is L and it's a small length. You have to find out the image length, let's say L dash. Now these are not lengths perpendicular to the principal axis. So the the normal formula for magnification minus V by U won't be applicable in this case. Minus V by U is for transverse magnification. Transverse means perpendicular to the principal axis. Okay, this is not transverse magnification. Okay, Anugrah, how did you solve this? You gave an answer.
Sir, longitudinal magnification is the square of lateral magnification.
Huh?
I-
Is there a formula like that?
Yes, sir. And then I did length of image is equal to magnification into.
Wait 1 second, but okay, fine. Fine, you seem to have been taught a lot of formulas. I never heard of a formula like that. Let it be, but let's think about it logical. Can you tell me how that formula was derived?
I'm not aware of that, sir.
Okay, okay. Fine, it may work in most cases. Like if you are given repeated questions, it will definitely work. But if you are given a new situation, then you have to think logically. Anybody, any idea how to relate L and L dash? And Anugraha, what if you were told that the object is of comparable, I mean, significant size, not a small object? Then also will you use that formula? Okay, we'll discuss. So listen, all of you, you are given the object size, you need the image size. You are told that the object is at a distance x from the mirror. You were not exactly told whether this end of the object is at a distance x, or the other end of the object is at a distance x, or the center of the object is at the distance x. You were not told anything like that. You need not be told anything like that because the object is very small. Okay, here for our visualization, I have drawn a significantly long object. But if it's very small, you don't have to be told which end of the object or which point of the object is at the distance x from the mirror. So just take the distance as x. So object distance is x. We can tell where the image will form, but we need to know how long the image is. Okay. So some random distance, I'll take it as x. Whether it is this end, that end, or the center, it's almost the same. Anugrah is asking, for any case for which the formula for later magnification is valid, this should also be valid, right? No, it will. I don't think so. We'll solve one more problem, you'll understand. And that's why you need to know how the formula is derived. Not just in this case, I'm telling this to all of you. Any formula that you learn, you need to know how it is derived, for which case it is applicable. Okay. Fine. We'll first find out the image distance. Let's call this distance as y. We'll find out how much that is. Apply the mirror formula, and we'll apply with sign convention. Okay, 1 by v plus 1 by u is equal to 1 by f. Or shall we take values? No need. Object distance is given x. If you substitute with sign, it should be minus x. Send it that side. You get 1 by v is equal to 1 by f plus 1 by x. F will be substituted negative. You don't have to write minus f. It will be substituted negative. Let's not get into that now. So this becomes denominator fx divided by numerator f plus x. Okay, Anugrah, in your answer, you gave f minus x. So maybe you took focal length with a negative sign. Not an issue. That is not the problem here. It depends on how they give you focal length in the question. If they give with positive sign, you substitute with negative sign. If they give negative, you substitute as it is. So I am taking it as it is, assuming they have given negative. Let it be. Therefore, image distance becomes fx by f plus x. Okay, we got the image distance, but that is not what we want. We want the length of the image. The idea here is, since the object is a small object, you take the green dot as one object and the yellow dot as another object. Okay, it's an extended object, no? So each point of the object can be considered as a separate object in front of the mirror. This is true in any case, even for objects placed perpendicular. That is what we did before also, no? The tip of the object is one point object. The base of the object is another point object. So an extended object is a collection of infinite point objects. You can take any one of the point objects. Okay. Now, in this case, when the object is placed perpendicular to the mirror, image also, not mirror, sorry. When object is placed perpendicular to principal axis, image also forms perpendicular to principal axis. All of them will be at the same distance from the mirror. That is not the problem. Here, different point objects are at different distances from the mirror. That's the issue. So you can take the green dot as one object, yellow dot as another object. The length of the object L is nothing but the difference between the green dot's object distance and the yellow dot's object distance. Do you all agree with this or not? The length L, which is the length of the object, is nothing but the difference between the object distances of the green dot and the yellow dot. Pradyumna, did you understand this point? The size of the object is the difference between object distances of its ends. Like you can call this as x1 and the other length as x2. The difference between x1 and x2 is L. Okay. And the difference between x1 and x2, because length is given to be small in this problem, you can just take it as dx, small change in x. Okay. Therefore, length of the object is nothing but dx. What is x? X is the object distance. So you can in fact call it as du. Okay. Length of the object is the small difference in the object distance. And length of the image will be the small difference in the image distance. We need a relation between du and dv. And how do you get that? By differentiating the mirror formula. Okay. If it's a small object, automatically the image will also be small. So small. Okay. Compared to the other dimensions. So differentiate the mirror formula. We know 1 by v plus 1 by u is equal to 1 by f. That differentiation also we had done before. Now we'll use that directly. Where is it? This one. Okay, this one. If you differentiate the mirror formula and cancel dt, you get a relation between small change in the image distance and a small change in the object distance. And in problems like this, where you are told that a small object is placed in front of the mirror, the length of the object, which is very small, itself is the small change in object distance. Okay, between the green dot and the yellow dot. And the length of the image, which is also very small, will be the small change in image distance between the green dot and the yellow dot. Small difference. Okay. So you can say that dv, the image length, is du, the object length, into minus v square by u square. Anugrah, is this the formula that you told?
Yes, sir.
Okay, fine. It works. You can use this. After this, I think solving the problem is not very difficult. The object length is given as L. Object distance is given as X. You substitute that here. Image distance you have to find out using the mirror formula and then substitute here. Okay. Is the idea clear to all of you or not? If you have any doubts or you want me to repeat, you can ask. Rishi, did you understand?
Yeah.
Okay. Isha, what about you?
Yes, sir.
Okay. Okay. So basically, see, such questions can be asked in any chapter. In fact, if you remember, we had solved questions like this in electric dipole also. Two dipoles placed in front of each other, or one dipole and one point charge. What is the force of attraction? I had asked you a question like that. So we know the field created by a dipole at a certain point, or we know the field created by a point charge at different positions of this dipole. So point charge will attract one of the charges of the dipole, it will repel the other charge, the distance between them being dx. So we'll write the electric field in terms of x and we'll differentiate it, we'll get dx there. The same thing they have done in optics. Okay, we know a relation between object distance, image distance. If you differentiate that, you'll get a relation between small change in object distance and small change in image distance. So for small objects, small images, you can use this relation. Okay, if values are given, you can substitute and calculate the answer. That is done. Let's try another problem now. Same situation, but this time the object's length is significant. Okay, Anugrah is asking when to take focal length as positive, negative. Like in this case, I have substituted it as f as it is. Actually, if they give you f, no, you take it as f itself because you don't know whether it is positive or negative. Then you have to use it as it is. If you know it is positive, you'll convert it to negative. If you know it is negative, you'll keep it negative. But if you don't know whether it is positive or negative, they just give you a symbol f. You use the symbol as it is in the formula. That is what I have done here. Suppose they gave you a distance like 30 centimeters, then you'll substitute minus 30 because you know it's a concave mirror, focal length is supposed to be negative. If they give symbol, take the symbol as it is.
So then why did you consider x to be
X
negative?
with a negative sign. Okay. It comes with practice only, I should say. Like, okay, what you're asking is valid only. I should not say with practice also. It can be taken minus x, it can be taken x as it is. But they didn't use, like, I didn't give the symbol u, no, so I didn't substitute u as it. X I took as the magnitude, but focal length I took along with the sign. What you are asking is completely valid. And in the question, in a proper exam question, such ambiguity should not be there. They will give you proper values, don't worry. Okay. So you will understand whether you are supposed to put a minus or not. Okay. Your doubt is valid only, but I took it like that because it's not given as u. Okay. Next problem. Suppose there's an extended object again placed along the principal axis. You know its image will also be extended. Let's say the focal length of this mirror is, how much shall we take? 10 centimeters. So the center will be at 20, and the object, assume object length. Okay, assume the object is like this time, quite long, significantly long. And where is it? The nearer end of the object is at 10 centimeters from the center. And the object's length itself is 10 centimeters. Find out the image length. Solve this quickly. Anugraha, do you realize that that formula will not be applicable in this case now?
Yes, sir.
Why will it not be applicable?
Because the length is
Not small. Yeah. So any of you tell me, how will you calculate the length of the image in this case? Any idea? If you observe the diagram clearly, you can get the idea. Okay. Can we use magnification as V2 minus V1 by U2 minus U1 and use mirror formula twice? Okay. Okay. Yeah, that is what you have to do now. Okay. You should find out where the yellow dot's image forms. So you have to find out image distance of the yellow dot. You can call it as V1. And you have to find out where the green dot's image forms. So image distance of the green dot also has to be calculated, V2. Their difference, okay, difference between their image distances becomes the length of the image this time. That is how you are supposed to calculate. So you should apply mirror formula for the yellow dot, find out where its image forms. You should apply it for the green dot, find out where its image forms, and subtract the image distances. That will give you the size of the image. And then you can find out magnification also. Is the idea clear? Rishi, did you understand?
Sir, can you explain it one?
See, what are you asked to calculate now?
So the length of the image.
Length of the image. Length of the image is nothing but the distance between the green dot and the yellow dot of the image. And the distance between those two dots in the image is nothing but the difference between image distance of the green dot and the image distance of the yellow dot. Do you agree with this or not?
Yes, sir.
That is what I told. You have to treat the yellow dot as an object, find out where its image forms by applying the mirror formula. Then you treat the green dot as a separate object, find out where its image forms. You'll get V2, and then you subtract V1 and V2 to get the size of the image. Okay, so if the object size is significant, this is how you proceed. If it's a small object like in the previous question, differentiation will give you the answer. Okay. Next. Suppose there's a point object only, and you are told that it is placed at some distance above this line. How will you find out where its image forms? If the point object is not on the principal axis, how will you find out the image position? That is my question. There's a point object which is not on the principal axis.
Sir, can we consider it as an object with some height and then find the height of the image?
Okay. Okay. That is how you are supposed to do it. See, actually, no, I told you this in the last class itself. A mirror has infinite number of principal axes. Okay, how you take the principal axis depends on where the object is placed. Now there's a point object that you are given here. You can call this as its principal axis if you want. Okay, it's still perpendicular. I mean, it's still perpendicular to the mirror here, and you can take the focus here at half of the radius. Okay, you can change the principal axis depending on the object, but that becomes very complicated. You'll have to draw exactly and all. Another way to do it is, as Anugraha said, you can consider the object, the point object, to be the tip of an extended object whose base lies on this principal axis. Okay, you can consider it like this. And you know, if object is beyond the center, image forms between center and focus, it will be a diminished inverted image like this. You know its image, the blue dots image will form here. Okay, that way you can find out where the image forms. You were not given the orange part of the object. You were only given the blue dot, which is off the principal axis. Okay, not on it. So you could have solved the problem this way. Just a moment, it won't be this big actually. It will be maybe from here to here. And this is where the image forms. Image of the blue dot. You could have solved the problem. I mean, you could have located the image by taking this as the principal axis. In that case, object lies on principal axis, image will also lie on principal axis. You can see below, the blue dot and its image both lie on that principal axis. Okay. Otherwise also you can solve it off by assuming it is the tip of an extended object. Okay. Next, okay, we are just discussing some ideas. Okay, you don't exactly have to solve it. Next, suppose there's an object given to you like this. This was one of recent JEE advanced problems. Okay, a rod is placed at some angle. They asked what is the angle made by its image. How will you find out? Angle made by its image with the principal axis. Exact position also you can assume is given. Okay. Let's say this distance is given to you, this end's distance, and this end's distance is also given to you. How will you find out how will you find out what angle the image makes? Okay, Anugrah has given one idea. Should we take the respective images and then take tan theta of the distances? Somewhat like that only. Correct. See, to get the angle made by the image of the rod with the principal axis, you just need to know where the ends of the images lie. That's all. Now, one end of the object is on the principal axis. Its image will form on the principal axis itself, somewhere here. The other end of the object is away from the principal axis. You treat it as part of an extended object like this. You know that its image will form somewhat like this, somewhere here. That's all. Connect them, you'll get the angle made by its image with the principal axis. So you'll need to apply the mirror formula and a little bit of geometry or trigonometry, if you call it. Okay. For the blue dot, it's easy. Directly apply the mirror formula. You'll get to know where the blue dot's image is formed. For the green one, you have to treat it as an extended object. Use the magnification. Then you will know where the green dot's image is formed. Then tan theta will give you the answer. Height of image divided by the distance between the blue image and the green image. That will give you tan of the angle made by the image of the rod. Okay, just think about this once again. Ask if you have any doubt. And just a moment, I'll find another question. Okay, so consider a situation like this. Mirror has been rotated about that pivot point by an angle. Okay, for convenience, let's take it 37 degrees because we know sine 37, cos 37 are easy to use. Find out the coordinates of the image. Exact coordinates of the image. Object coordinates are given to you. You know how the mirror is arranged. Yeah. Okay, tell me ideas first. Exact solution will take time actually. I mean, you have to find out the distance, use a little bit of trigonometry, mirror formula, again use a little bit of trigonometry to get the exact x coordinate and y coordinate. That's fine. But can any of you tell me the idea? How are you going to find out the coordinates of the image?
So for coordinates, can we apply the mirror formula separately for x coordinate and separately for y coordinate? The distances d and du.
See, the object is on the x-axis. It has only x coordinate, doesn't even have a y coordinate.
The image might have y coordinate.
But if object doesn't have y coordinate, how will you get image y coordinate?
If we substitute 1/0, okay, it will be infinity.
Okay. See, there was a question like, you have seen that other question. Lens was also involved, but put it aside. But many of the books, they wrote solution based on something like this. They considered an object like, see, the tilted line is the principal axis for this mirror. They considered it like that. Nothing wrong in that. It's perpendicular to the mirror. You can take it as a principal axis. Nothing wrong. They took the object as an extended object. Okay. Now see, that angle is 37. This angle is also 37 degrees. So you can find this object distance. You can find the height of the object also. Both are known from trigonometry, can be done. Then what they did is they found out the image height and then applied trigonometry again. Kind of like how this object is significantly far from the mirror and it's a convex mirror. No, convex mirror has only one case of image forming. It will form on the other side only and it will form between center and focus. What am I saying? Between pole and focus. Okay. So they found out the image coordinates, image where it will form, image height they found out. And then they wrote the coordinates of this image point. It may be on x-axis, maybe above it, below it. I don't know the exact answer. I mean, we have to solve. But there is a flaw in this approach. Tell me what is wrong in solving this problem this way. Suppose you know all the mathematics to do this. Still, what is wrong in the physics that we have applied here? What is wrong with the physics that we applied here is that this angle 37 degrees is a significant angle. Okay. So if you take this as the principal axis for this mirror, then the rays coming from this blue dot will not be paraxial rays. Paraxial approximation itself is not valid, means the mirror formula itself won't be valid. If you consider it like this, you should not. For objects of such large heights, you cannot use the mirror formula and find out the height of the image. Okay, because whatever we have derived till now in optics is all based on paraxial approximation. That's why I told you it's very important to know the derivations, the conditions under which the formulas are applicable. Okay, I'm telling this to all of you. So that is what is wrong with this approach. You can't just find out the image position, image height and tell its coordinates. Okay, because the angle is not a small angle. Then what to do? Like if you ask me, the correct way to do would be to draw a new principal axis passing through this object. How do we do that? we know where the center of the mirror is. So you will have to draw a line connecting the object and the center. This becomes a new principal axis. Based on that, you have to find coordinates, which will be a very lengthy procedure actually, because now you don't even know where the pole is. If you know pole, then you will get object distance and then you will get image distance. You don't even know where the pole is. Pole is not at the origin this time. But this is the correct way to solve. You can't treat it as an object of this length and find out the image position. It won't work. Okay, anyway, I just wanted to tell you what is the correct approach to take. You have to be cautious about the angle also. Okay, this is an advanced problem. This was an advanced problem, somewhat similar like this. I don't know if it was challenged that year or not, but this is the correct way to solve it. Okay, fine. We'll stop it here for now. Tomorrow I'll give you a worksheet based on some ray diagram. We didn't discuss any case based on convex mirror. Let me okay, I think we have drawn the ray diagram for a convex mirror also. It has focus on the other side, positive focal length. If it's an extended object, no, say something like this. For a convex mirror, there is only one kind of image that it can form. If the object is real, there's only one kind of image that it can form. Let me quickly show you that. Because while solving problems, you need to imagine the ray diagram. Then only your answers will be correct. Why did all this get copied? Okay. Yeah, so we know where the focus is and all. Parallel ray after reflection passes through the focus or gets reflected as if it is coming from the focus. That's the correct way to say it. And another ray, take it directly to the pole, it will get reflected symmetrically. Symmetrically means it should be passing through this point. Okay. And it appears as if it is coming from somewhere here. This is how the image forms. And a convex mirror always forms this kind of image only. Diminished, upright. It's on the other side of the mirror, so it is virtual. Upright or erect, diminished image. Okay, and in fact, this is the reason why convex mirrors are used as rear view mirrors. Okay, in vehicles, side view or rear view. Okay, because they form diminished images of the objects in the same orientation as they actually are. Okay, so when you see in the rear view mirror of a vehicle, you would like to see what's behind you in its same orientation. You wouldn't like to see upside down images, no? And also, a rear view mirror is supposed to have a large field of view. Okay, you should see a lot of what is happening behind you in that small mirror. So if it forms small images, no, it can fit in more information into that region, into that space. So this is how this is an example of an image taken in a convex mirror. You can see that almost the entire room of the person, its image fits in that small mirror. Okay, so they're all diminished, as you can see, diminished images and upright images in the exact orientation as they, in the actual orientation in which they are present. Okay, we'll discuss this a little further, why convex mirrors are used as rear view mirrors and what kind of mirror a dentist has to use. All those things we will discuss in the next class. But remember, for a real object, a convex mirror always forms a virtual upright diminished image. Okay, thank you all. We'll continue on Tuesday, usual class.